Welcome back, quantitative analysis students. This is Mr. Marquetta. Today, we're going to talk about logarithms and exponents. And I have to be honest, this is one of my favorite lessons because logarithmic expressions are probably the ugliest that you would write in math, but they happen to be, in my opinion, probably one of the easiest ideas. And a lot of students feel a lot of success when they study logarithms because they feel like, oh, math isn't so bad after all. I know it's far-fetched, but it's true. Logarithms, when you're able to do them, it kind of makes you feel a little bit more confident. That's kind of why I like logarithms. Anyway, exponents and logarithms are inverses, like plus and minus, and so on. You divide and multiply. Inverses, logarithms and exponents are inverses. Today we're going to talk about a little bit of a review of how logarithms work, because not everybody remembers all those wonderful little stories about logarithms, like what if there's a product, what if there's an exponent, and all those things. But then besides that, we're also going to talk about how to find the derivative of a function that has a logarithm in it. And we're going to talk about special logarithms like the natural log and the common log. And then we're going to talk about how it was figured out that the natural log is connected to 1 over x. The derivative of it is going to be 1 over x. And we'll talk about that too. Then I'm going to do it with exponential functions. And again, Euler comes in. Euler was a very talented German mathematician who discovered an amazing number. The number is E, and it is an irrational number between 2 and 3, and it is used widely in the sciences and economics whenever logarithms are used and applied, because it represents the best version of a base of logarithm. When you could choose any base, this is the base that works the best in certain situations. So the natural logarithm is based on E, which is the number that was found by Euler that I just explained, between 2 and 3. So let's get started by talking first about logarithms and try to remember some of those old logarithmic stories. Here we go. If you take a look at y equals natural log of x, it's going to look like that when you graph it. Students like to call it a boomerang. It looks kind of like a little bit of a curve or a wave, whatever, however you want to look at it. But what we're going to talk about today is the natural log of x, which is a log with a base of e. When you talk about logs, though, and we have to talk about the mechanics of logs a little bit, because I just want to make sure everybody's comfortable with those ideas. When you talk about a logarithm, and I'm focusing on this piece, you say this out loud as y equals the log based a of x. And the a is called the base, and the x is called the argument, and the y is actually the power, because logarithms ultimately are just powers. In fact, logarithmic talk is all about exponents. And if you start adding them or subtracting them or multiplying them, you're really just multiplying exponents in an abstract way. So in the same way that those variables hold in that statement, y equals the log base a of x, they also hold in this statement a to the y equals x. And if you look at the second statement, it's a lot more comfortable for us. I understand statements like 3 squared equals 9. That makes sense to me because I know what exponents are and how they work. 5 squared equals 25. Like if I had it in that way, it would make sense. But now if you can apply those same numbers with that same fact, that 5 squared equals 25, but you could apply it to a logarithmic expression, instead you would say something more like 2 equals the log base 5 of 25. So like, in other words, 5 to the what is 25? And the answer is 2. Those three numbers, 5, 2, and 25, are connected in an exponential or inverse logarithmic way. The same way a subtraction problem has an alternate version in addition, So logarithms are basically a way for you to solve for the exponent. Ultimately, that is the point of a logarithm, because whenever you have a variable up in an exponent, it's hard to isolate it in an equation, and logarithms are really the primary reason for them is to get them solved and get them out of equations. But more so than that, they're used in different ways in economics and the sciences, like I told you. And in the case of the base, you could have a log base 2 of x, a log base 15 of x. If you have the log base 10 of x, it's called a common log. And if you have the log base e of x, you don't call it that, you call it the natural log of x. And again, e is that important number that Euler discovered. So what we're going to do now is just kind of refresh a little bit about these ideas that you have down here. I'm going to explain them for us. I'm going to get rid of those rectangles. I'm going to explain all these ideas for us and give you some brief examples. It should take maybe 15 minutes, kind of just a refresher to remember, because here in quantitative 2, we kind of assume that you've already studied it in a math class somewhere where you went through logarithms, but I would never assume that my students were all experts at logarithms if I was teaching. So I think it is appropriate to go over just a 15-minute review. So I'm going to explain them, and please make sure you let me know if I can explain them in any other way, because they are easy ideas, and it just is a matter of really grasping them and being able to move on from them. Because if you really get all of the ideas with logarithms, then when you do the derivatives of them, you'll have an easier time. So these rules apply. We're going to go through all of them. I've put together a little lesson I'd like to share with you. Let me do that now. All right. So if everybody's looking here together with me, if you could go to the top right where it says view and make sure that you've clicked speaker view so that way you're looking at primarily this image. This image is pinned. This video is pinned. This is as if I had a student speaker. So we're going to use this. I've made up some examples here, and then I have all of our examples from the chapter 11.1 and 11.2 derivatives in here too, and we'll go through them with writing. Starting with the basic concept of a logarithm. As a reminder, you have a basic structure that you have a number like a b base that is raised to a power p, and the answer, we like to call it the argument. Different textbooks will call these things different terms. You have, they like to get creative. When you read a calculus book or a pre-calc book, you'll see them call them different things. I remember in one book they called this the argument, and I thought that was the best word to use to describe it. So a number like 2 to the power 3 equals 8. 2 is the base, 3 is the power, and 8 is the argument. Then we could rearrange these letters or these three numbers that have this connection that we talk about in a logarithmic way, such that we're telling you straight out something about the power. See, here we're telling you something straight out, something about the argument. Here we're telling you what the power is. The power is a logarithmic connection between b and a, where b is the base and a is the argument. So one easy way to try to solve a logarithm when you're looking at it is to think to yourself, if this is the base and this is the argument, then you could say, well, if I took this thing, what would I have to raise it to in order to get this thing? And it's kind of a puzzle. It's a little bit of one of those backwards, like a backwards brain teaser thing. Like, remember when you learned about division and you had to rely on your times table facts? It's the same feeling because they're connected in the same way. They're inverses, exponents, and logarithms. So, in the case of 2 and 16, you might think 2 to the what is 16 and arrive at 4. That means that it equals 4. P is 4 in that case. And if you wanted to do some practice, you could take a look in your textbook in chapter 0.6 and 0.7. There's a lot of great examples there from high school pre-calc or college algebra that you might have taken already and you want to refresh. You can go practice them. I have a couple of them here I want to just share with you. Here are two cases that should be obviously connected. If we'd like to say that 4 squared is 16, it's the same statement as if we were going to say the log base 4 of 16 equals 2. See how 4 is small and it's a subscript? And the 16 is a regular sized font. There is kind of a feeling of an upward motion here going up toward that 16. If you can think about moving in that line and saying 4 to the what makes 16, then what will happen is you'll be able to come up with that 2 as your answer. Like 4 to the what makes 16, it's 2. You want to be able to quick trivia, you could say something like this. You would say, well, what's the answer to that? If that's the log base 3 of 81, if you say, well, 3 to the what makes 81? The answer is 4, because there is an alternate statement. 3 to the 4 equals 81. So they're always two. It's a pair of statements when you look at an exponential or logarithmic expression or equation, because it ultimately is two statements at the same time. In the case of the first one, 4 squared equals 16, that's very simple because those numbers are easy and very basic. We already knew that 4 squared equals 16. Let's get more abstract. What if they throw ugly ones at you? And welcome to calculus and quantitative analysis too. They will throw ugly things at you. I made up an ugly one. We do have, of course, here a base. And of course, here we have a power. And then here I have my argument. So if I just blindly rearrange them and write the word log and put everything else where it belongs, then it turns into this. The log with the base of x, given the power, given the argument, given the argument 8x plus 8, and then with the power being 5y. So you could see how they connect. And it's important that you're able to go back and forth between the two of them, right? You can see all that. All right, so here are those formulas again, and without giving away the big ending here, here are the ones that we're going to go through first. You've already learned most of them. You might just need to remember them slightly, and I'm going to go through each of them. And then here are all the derivatives as well. The three derivatives we're going to talk about today are, if you wanted to find the derivative of the natural log of x, it's simply 1 over x. And now you can apply the chain rule to that. If you had the natural log of an expression, it would be 1 over that expression, but then times the derivative of what's inside, as if it was a chain link at the end, like the chain rule. Another odd case, the derivative of e to the x is going to be e to the x, and it's kind of ironic and silly, but there's all kinds of jokes in math about how when you take the derivative of anything, it changes it, but when you take the derivative of e to the x, you get e to the x back. And there's a weird poetic statement about it. Then you have a to the x. A to the x is if it wasn't e, but something else. Maybe your derivative is 2 to the x, or 14 to the x, or it's 14 to the parentheses, a big expression. Well, then the answer is just like e to the x, it's again a to the x, but also times the natural log of whatever a was as well. So that's how they basically correct it. And it does apply also to the middle rule, because the natural log of e, if you think about it, e to the x natural log of e, the natural log of e is actually going to be 1, and we'll talk about why that's true when we get to some of the easier log rules. But first, let's do the more advanced log rules. We could leave this for a little while, and we'll get to this later, but we're going to focus on logarithms now. Before we do calculus and derivatives of logs, we're going to do the old school logs rules. The first one is, if you have a log and you have a base that is a, and you have an argument that is a, and then there's a power of x, the answer is just x. In other words, it feels like it almost cancels out, as if you could cancel the a's out, and you're just left with x. In terms of natural logs, which instead of writing log base e of x, instead you write ln of x. And when you have the natural log, that means the base is e. And if we have e and x like that, again, we get just that x again, like we did before. So these two are connected. This is how it's written for all other bases. This is how it's written for the base of e. That's the reason why ultimately ln of e is just going to be 1. Here we have the same thing, but in a little bit of a backwards motion. We have a to a power, and the power is this complicated logarithm with a new base of a. It's as if these a's cancel out, and you're just left with x. It translates to e to the ln of x, turns into x. So for parts 1 and 2, these are very odd specific cases that are based on the concept of an identity property, where it comes back to the simple whatever you're looking at. So if you had the log based a of a2 and there was some funny expression there, the answer would be just what that funny expression is. In the case of this x, it's the x that you see there. So it's thinking of it like canceling out and collapsing all the way down until it's just what the original thing was left over, the x. The last 3 are connected in a way that feels like you're in PEMDAS, but just off by one or two rungs of a ladder. Like if you understand PEMDAS, right? PEMDAS is parentheses, exponents, multiply, divide, add, subtract. I know you all remember that, right? But if you think about how when you're multiplying, it becomes adding, you'll see that it kind of has a connection of 2 rungs down. When you're dividing, you're subtracting. Again, it feels like you're doing 2 rungs down. Look at that. And when you're doing the exponent, you actually wind up multiplying. Again, you're doing 2 rungs down. Something funny about logarithms is that it does kind of apply the PEMDAS algorithm in a symmetrical way, that what you have is always 2 steps behind what you were. So in the case of when you're multiplying logarithms, like you see in case 3, if you're multiplying if you have a logarithm where the argument is 2 things multiplied, you can split it up, but you use a plus there. You might think that is a multiply, so that should be multiplied, but it's not. If that's multiplied, that should be plus. It's like 2 rungs down on the ladder of PEMDAS. Same thing with division. If you see 2 things being divided here, or if it's written like this, and you have stuff up here and stuff down there, you could write it so that it is the first thing on top minus the second thing on bottom. And again, that is a case of moving in 2 steps on the PEMDAS algorithm. Then, of course, if you have something to a power or an exponent, you could take that power and kind of bring it right to the front and put it right in front of it like it's a new multiplier, as if it's a coefficient. This is a connection from exponents to multiplication, again, 2 steps down the ladder from PEMDAS. Right? So when we see, in the case of the argument has a multiplier, whether it's natural log or any log, we use plus. When we see division, we use minus. And when we see a power, we make it the new multiplier in front. That's the story of how you can expand and contrast different logarithms when you need to. And you'll see in the exercises, it'll be more practical to expand them or to contract them before you take the derivative, because if you take the derivative otherwise, it creates such an uncomfortable, difficult case that it's on you to know which path to go to. Should I do it, or should I simplify it, or not? Or should I leave it the way it is and take the derivative? Sometimes you should, and sometimes you shouldn't. So you should know all these rules, and they might pop up a little bit when you're doing the practice, okay? Once more, these new functions we're studying, the natural log of x, e to the x, and a to the x, have derivatives as such here, and I'll be coming back to use this to try to explain some examples. Let's do some cases. Here's a case. When you have two things, the base and argument are the same, and you see a little power up there, you can imagine it's like they cancel out almost. The answer is just x. Same thing here. If these two things are the same, they cancel out. So what's left here is what the answer is. Okay. And by the way, I just want to make a mention about b. If you look at how it's adorable with the 777, be prepared, especially in WebAssign, when you do your homework, to see very strange looking, almost blinding looking expressions that make you kind of shake your head a little bit. They are trying to make it complicated, and it's on you in math to be able to understand what it means. This is a subscript of 7. This is an argument of 7. This is the power of 7. They're all funny sizes and in different places. If you understand the construct of a logarithm, you should be able to understand how those numbers are connected. Right? Here we have e to the ln of 5. E and ln should cancel out, so you should have just a 5. Here we have 13 to the power of a log that has a base of 13. Again, they feel like they cancel out. So whatever is left there is the answer. Like that. And then here, once again, the natural log has a base of e, and we have an argument of e. And then we have something up here. This right here is the answer, because these cancel out. The answer is just what you see there. I'm going to leave this here for a minute. These 5 easy logs are the ones that they should pop out as very simple. You should know, I know what that is. For a, oh, that's just x. Look at c, that's so easy, it's just 5. Like they match, and it looks like they match, and it's actually just what you think it is. And in part D, that 13 and 13 log, they just cross out and you just have x minus 2. I want you to come back, friends, and look at this again when you do when you practice in WebAssign. Some of them are actually that easy. I think in math, often students will look at something that's really simple and say, no, it can't be that easy. And they make it harder and screw it up and get it wrong. You know, these are some very easy little ideas, and when you get to them, you should know how to operate using these little rules. This is rule number 1 and 2 being applied that we talked about before. And then this is going to be rules 3, 4, and 5 that we have, which is that idea that if you're multiplying, you're supposed to add. If you're dividing, you're supposed to subtract. And if you have a power, you're supposed to make it multiply. So here we have some great cases of it. Let's talk about how you would expand these logs. The first one has a case of a multiplication going on right here. So what I do is I'd write the log as a sum with using a plus. Now, when you do it, make sure that you include that base every single time. Don't forget that base. Now, x squared, this exponent, based on that rule where you can take the exponent and put it in front, that means that really we should be putting the 2 here instead. So it should really be log base 2 of 5 plus 2 log of x. This is what we would expect you to come up with if we said, can you please expand it? Notice there's 2 expansions. The first expansion is that here we're looking at multiplication, which means let's add. Then likewise, we have here, we have an exponent, which means let's multiply there. It's the 2 as a multiplier, okay? Now, let's talk about part B. Part B, we have log base 7, and again, we have a case of division. For the division, we're going to say it's the log base 7 of 3x minus the log base 7 of 3 plus x. Now, when you have, what I did, 3 plus x, that's supposed to be. When you have something like that, you can use parentheses just to make sure that you know that we're not talking about the log base of 7 of 3 there. But then when you're through with that, notice here we have a multiplication. That can be changed in the same way that this was changed up here originally. Here we have an addition. I want to remind you, there is no such law for the log of m plus m. Look closely. There's no such law. There are only laws about m times n, m divided by, or m to the power of something, and then these little ones. So whenever you see the natural log of x plus 2, don't let them fool you. You can't do anything to that. You can't simplify that any more than it is. If it was multiplied, you could. The point is, in this case for part B, this can get brought down more, but this cannot. That's got to stay the way that it is. All right, let's split this up. And now it ought to be log base 7 of 3 plus log base 7 of x minus log base 7 of 3 plus x. And I'm running out of room. All right, very good. That's the solution for part C. Let's look at this one. In this case, we have a 9 as an exponent. The 9 as the exponent should be the multiplier. Should be 9. And you might see that this is a multiplier in here. So that should be actually like plus. So I'm going to put the 9 in front, and then I'm going to use square brackets. I'm going to put 2 logarithms here. It's the log base 4 of 6 plus the log base 4 of x. If you want, you could distribute the 9. You know how to do the distributive property. 9 log 4x plus 9 log 4 6 or whatever. You don't have to. You could leave it that way too. Depends on what you're doing. But if you were supposed to go further, you would make it that equals 9 log 4x plus 9 log 4 6. Okay, for this one, we have the log base 6 of x. I'm kind of running out of room, so I'm going to use a new paper for it. Doing this one, log base 6 of the square root of x, you should know the square root of x is, of course, x to the 1/2. So, as an exponent, that means it should go out in front like so. This is what we'd expect for you to get for that last answer. This other one, log base 3 of 1 over x, you could do this in a couple ways. The best way to do it is to change it to its exponent. The exponent is x to the negative 1. And if that be the case, this exponent can be the new multiplier. Like so. I want to just remind you guys, this is what happens when you have a square root. When you have a square root, it means 1/2 power. So in the world of logarithms, you have a 1/2 multiplier. If it's a 1 over x, remember that means x to the negative 1, so it looks like this. To be formal and practical, you really shouldn't write that 1 either. Not that it really matters, but if you really want to simplify it, the idea is write as little as possible. You don't need that 1 there. So that's how you would do those. All right. So help a little bit because that's everything you really kind of need to know about logarithms. And now that we've done that, like I said, I thought that would only take 10 or 15 minutes, and it did. Right. Now let's take a look at what they're expecting from us. Here are some examples that we're going to go through today. These 3 examples each have sub-examples, and it's a total of 7 different problems. I'm going to go through them one at a time, and we're going to rely heavily on these concepts. That the derivative of the natural log of x is 1 over x, the derivative of e to the x is just the same e to the x, and then the a to the x derivative involves ln a. That stuff that we talked about is going to be used all through these examples. What I did was I already wrote the examples here, so we're going to just kind of go right to the paper and try to get through these derivatives. I'll explain just how to do them for you guys. Starting with example 1a, at first we have a sum. It's an example of a sum. So since it's a sum, we can act like the 2 things being added, x cubed and 3 ln x, are 2 different things, and I can take the derivative of those 2 things separately. So first, let's write out that we mean to take a derivative, y prime equals, and now what's the derivative of x cubed? We learned already that's 3x squared. And then we have 3 natural log of x. So Recall that the derivative of the natural log of x is 1 over x. And recall that if you have a coefficient, the coefficient rule says you can ignore the coefficient for a minute, do the derivative of the expression, and then when you're done with that derivative, come back and multiply by the coefficient again. So we'll ignore the 3 for a minute and say, now what's the derivative of the natural log of x? Well, it is 1 over x. And now, by the way, that was times 3. If you have to write it like that for a minute, that's fine. Simplify it. Now we're finished, and we get 3x squared plus 3 over x is your derivative. Okay? So it's just a new little factoid. The derivative of the natural log is 1 over x. There's a long story behind why that is the case. Read the chapter, all right? And it'll explain in there what that's about and why, especially when you try to take the derivative of, when you start learning about integrals, it makes a little bit more sense. But right now, that's kind of a given. You have to just, the proof is kind of hard to follow. Anyway, for example, 1b, it appears I'm looking at an example of a product. I have x squared times the natural log of x. So what I'll do is I'll follow the product rule. Let's recall the product rule. The product rule states that if you have two things being multiplied and you take the derivative of them, that you have to write it out in this format, fg plus fg. And the first one f is prime and the second one g is prime. So if I was going to apply that to this case, I would start by thinking about how x squared is f, and the natural log of x is going to represent g. That implies that f prime is 2x, and g prime is, of course, our basic lesson today, 1 over x, because the derivative of the natural log is 1 over x. Now we'll assemble the derivative using the product rule here. It's f prime g. So this was y. So we'll call this y prime now. Y prime is going to be f prime g, which is 2x times the natural log of x, plus f g prime, which is plus x squared times 1 over x. Now x squared times 1 over x, you should know, you could put that over 1 if you wanted. It becomes, do a little think bubble here and think about that for a minute. That becomes x squared over x. And isn't that like xx over x? That's why it's just x, kind of abstract, but it's just x. Which means, in other words, this derivative is 2x ln x plus x. There you go. I told you it wasn't that hard. I hope that makes sense. Example 1b, finally, you're involving a little bit more advanced derivative rules. You have the product rule. And in the product rule, it's just a matter of really defining them. I'm telling you, if you write them out, it makes it real easy. If you can do them in your head, some of us can do them in your head. If you get good at them, you start to do them in your head. But however you want to do them, this is how it works. And the only new curve to the story is the natural log of x. When you get to that part, the derivative of that is going to be 1 over x. All right, here's the next one. In this case, we're applying the chain rule. The reason why is because it's not the natural log of x, it's the natural log of a bigger expression. In this example, we're going to pretend for a minute that x, or the cloud, is the expression x to the 4th minus 3x over 7. So the derivative of the natural log of something is going to always be 1 over that something. So if it's 1 over that something, it's going to look like this. And then times the derivative of what's inside. What's inside this time, the derivative of that is 4x cubed minus 3. And then the derivative of 7 is nothing, or 0, because derivative of all constants, remember, is 0. Now, once again, like before, when you see a fraction times an expression, you should clean it up in this way by putting the expression you have over 1 and then multiplying across, giving a new expression like this. Okay, I hope that makes sense. Yep. So did we do that right? Yes, we did. We thought about the natural log of an expression. We took the derivative of it by making it 1 over that expression times the derivative of what's inside. Inside was this expression. The derivative of that is 4x cubed minus 3 and then we combine them. Whenever you do a derivative, friends, you should just run through it one more time in your mind before you submit it for sure, because there's a chance that you messed up something small. For example, we all know 4 times 3 is 12. But in the middle of all this crazy logarithm stuff, you'll write 4 times 3 equals 16 and you won't even know it. It's just human. So if you make a little mistake here and there, it's not a big deal. You really can always catch it though. If you just give it a couple more seconds and just review it one more time before you say, yeah, that's it. It's definitely this weird looking thing, 4x cubed minus 3, whatever that is, right? And so I would recommend you just review for a minute afterwards to make sure you're on the right track. All right, so we're going to do that again for example 2b. In example 2b, it's basically the same story, except it is involving also the coefficient rule. Now recall the coefficient rule. Coefficient rule says if you're taking the derivative of something, and there's a coefficient, you can ignore the coefficient and just take the derivative of that thing. And when you get the derivative, bring the coefficient back and put it in front like in the new coefficient. So we're going to ignore 1/3 for a minute. And we're going to go through the motions of finding the whole derivative of that whole natural log. So what is the derivative? It's going to be, and by the way, we should write that it's not the same as the function, f prime of x. I'm just going to write 1/3 and leave it there. And now I'm trying to figure out the derivative of the natural log of this thing. Well, the answer is going to be 1 over that whole cloud. Then, because of the chain rule, I have to add another link to the chain, which is the derivative of what's inside. This time, this is what's inside. So inside there, we would do the derivative of 2x to the 6th. That would be 12x to the 5th. And then the derivative of negative 3x, again, that's the coefficient rule. Coefficient rule says derivative of negative 3x will be negative 3. And the constant rule tells you the derivative of 2 is 0, so we don't have to write anything. Now, we can make this a little bit nicer. First of all, if you put this over 1, you might be clever and notice that this 3 right here is actually a factor of this expression. I could factor 3 out of there, and it would look like this. 4 times x to the 5th minus 1, right? Because doesn't that multiply back? So let's knock them out. That 3 goes with that 3, and it's supposed to be this now. So my new numerator will be 4x to the 5th minus 1, and the denominator is what it always was, 2x to the 6th minus 3x plus 2. That's what I do this time. All right. So it looks good. I ignored the 1/3 for a minute. I left it there. Later on, I was able to use it to knock out a little bit of this. And I reduced it. I think you guys know when you do WebAssign, if you don't do that, it often will accept your answer. So if you could try it, but you should know ultimately it's supposed to be reduced. And then, of course, just remember whenever you see an expression, you can write it over 1. Often I include parentheses just because why not? Like when I was here, I put parentheses. If you ever feel like that's going to be a little tricky to write, you can always use parentheses. They save you a lot. All right, so that's example 2b. For example 2c, we're going to connect the quotient rule with our logarithm derivative now. Let's recall the quotient rule. The quotient rule is if you have a quotient like f over g, and you take in the derivative of it, it would be fg minus fg all over g squared. But you want to take the derivative of f in the first case, take the derivative of g in the last case. Right. So let's take a look now at g of x here and see if we could find the derivative applying this quotient rule. If we were applying the quotient rule, I would start with the numerator being f by saying f equals natural log of 2x plus 1. And then g would be the denominator. So g is 2x plus 1. Now, the derivative f prime here of the natural log of anything is whatever that anything was, 1 over that, whatever that was. Now, don't forget, times the derivative of what's inside. What's inside? Inside, we have 2x plus 1. The derivative of 2x is 2, and the derivative of 1 is nothing, so it's just times 2. So isn't that going to really look like this now? Oops, what happened? Why is that 2? That should be a 1. Let me write that again. It should be 2 over 2x plus 1. like that. All right, so that's what f prime is. And last but not least over here, g prime, of course, will be 2x, and derivative of 1 is nothing. So now I have f, g, f prime, and g prime. Now I can write the derivative. So the derivative will be g prime of x is f prime g, which is 2 over 2x plus 1 times g, which is 2x plus 1, minus fg prime, which is this expression, natural log 2x plus 1. And g prime is 2x, so I'm going to write it like this. And that's all over g squared, which is 2x plus 1 squared. Now, I'm going to need to simplify a little bit more. There are some things that really pop out easy, like, for example, can you see 2x plus 1 and 2x plus 1 here knock out, right? So that's just 2. And likewise, I could put the 2 in front of here. So just to simplify that a little bit more before we go on to the last one. That would just be now g prime equals 2. That's that 2 minus. And now here I'm going to write 2x in front. It looks a little bit nicer. 2x natural log of 2x plus 1 all over 2x plus 1 quantity squared. All right. So if you were going to simplify this, just one more step, you get to this. Now you can see these are big questions. There's a lot of work in them, and it really does require mastery of fractions and stuff. In this situation, I want to mention also, just like the 777 thing I showed you earlier, often they like to try to tempt you to do the wrong thing. Like, for example, you really might want to cross out 2x plus 1 here, but you really cannot. And the reason why you can't is because this is the natural log of 2x plus 1. This is 2x plus 1 down here, not the natural log of it, but the actual idea of 2x plus 1. There is no connection between them. You cannot cancel them out. If you try to cancel them out, you're going to get it wrong. You're going to, you get points off and stuff. So just be careful about what you can do and what you can't do. Often in calculus, they set up a question that brings you to a point during the solving of it that makes you think, oh, I know, can I cancel that? That looks like I should be able to cancel it. And you do, and you mess it up. So here's a great example of a time when you should not cancel and you're kind of tempted to. The correct answer is what you're looking at here, and that's it. Okay. That's example 2C. Let's do example 3A now. Here we're taking the natural log of a product, the product being x, and then this whole expression with parentheses to the 10th. In that case, the way we deal with it is, the first thing it really is ultimately is a natural log. So we're going to treat it like a natural log. And then when we do the chain rule and add on the new link, that is the derivative of what's inside, then it comes into play that this is a product and we can use the product rule. So to get the correct answer for this, first we have to write out the idea of a natural logarithm. Remember that the derivative of the natural log is going to be 1 over whatever is in that cloud there. So if this whole thing is what's in the cloud, then the derivative y prime is going to be that whole thing underneath 1, like this. Just the way you see it, even though it's very complicated, it feels like you're really not even doing anything. You're just copying it. But you have to write the whole thing in that way to follow this structure, okay? Then we have to figure out now the derivative of what's inside, which means now we're in a position to try to use f and g in the case of the product rule. Here's the product rule again. If you're taking the derivative of two things being multiplied, then you could do it this way, fg plus fg, making the derivative on one and then on the other, like so. So in this case, thinking about just this expression here, it would be f equals x. And I'm going to kind of leave this for a minute. F equals x. And then g equals this whole thing, x to the 5th minus 2 to the 10th. real dichotomy there, very, very simple, just x and then g, which is this big expression here. We come down to a trivial concept. What is the derivative of x? And it's could be a real mind boggler. It's basically a factoid, and you have to always remember the derivative of x is 1. And the reason why the derivative of x is 1 is because of the coefficient rule. In the case of the derivative of ax, the answer is just a. So if it was x, it's kind of like 1x. The derivative of 1x, of course, is going to be 1. All right. So that being told, we can now safely assume f prime equals 1. Then to get g prime, we're going to apply the power rule. Remember the power rule? The power rule says, let's see, I'll put it right here. X to the n, if you take the derivative of that, you're going to get n times x to the n minus 1. That's the power rule, right? So if we're going to apply the power rule, we're going to have to also use the chain rule, because this is not x to the 10, it's an expression to the 10. So we're going to write 10 times the expression. And then if n is 10, then 10 minus 1 is going to give a 9. So 9 is the new power. And last, we have to multiply by the derivative of what's inside. What's inside is 5x to the 4th. And then minus 2, the derivative of a constant is nothing. So just to simplify this a little bit more, g prime, I could take the 10 and the 5 and the x4 and move them around a little bit to make it look like this: 50x to the 4 times x to the 5 minus 2 to the power 9. So g prime, as you can imagine, became this really large, ugly expression. The g itself was a pretty big, ugly expression. X, of course, is very simple. We have a nice connection between basic and advanced here going on. Now, remember, the whole purpose of this was because we had to find the derivative of what's inside for this logarithm case. And inside is that expression, the derivative of that. We can come up with it and assemble it if we use the product rule. And the product rule is here, and we have all of the things we need for it. So now let's write it in. It would be f prime, which is 1, times g, which is this expression, plus f, which is x, times g prime, which is this thing. Looks like a lot, doesn't it? Let's make it a little bit more clear on a better piece of paper. Taking it from there, y prime would look like this. Still can't fit it. So you can see this whole thing is really supposed to be up on top here. And likewise, I have here an x along with a 50, x to the 4th. These things can be combined as well. Instead, it should look like this. X to the 5th minus 2 to the 10th plus 50 x to the 5th times x to the 5th minus 2 to the 9th. All over this expression x times x to the 5th minus 2 to the 10th. Now, even using a notebook paper, it's challenging to write this stuff because it fills up the page. Trying to do this in your head really very challenging. I really recommend you get a notebook and a pencil and try to work through it. I just want to review with you guys once more, okay? What we did was we were trying to find the derivative of this expression that involves the natural log. And when we did, we first applied this concept that the natural log derivative is 1 over whatever you see. So it's 1 over that. And so here's that expression. Now, the chain rule says we have to take the derivative of what's inside. To take the derivative of what's inside is a whole other story involving the product rule this time. And we have a 10 there, so get ready for some more advanced work. In this case, x is going to be f, and x to the 5th minus 2 to the power 10, all of that is g. We're going to follow this structure and try to figure out the product rule, try to find the derivative using the product rule. So after we determine x and g, f and g, then we determine f prime, which is just 1, and g prime, which is this complicated expression here. And then we put together this expression, the derivative, using the product rule, and it becomes this. What I did after that was I rewrote it to be a little bit more clear here. And notice that in this part, we can connect this x to the 1 and x to the 4 to make x to the 5 that I have right here. And if you have 1 over something times an expression, remember how we said many times already today, if you have an expression multiplied by a fraction, that expression is over 1. That's why it all belongs in the numerator. And if you simplify it, this is what we get. Again, not the most comfortable expression, but this is the stuff we're studying here in quantitative 2. Example 3b is, as you can see, definitely a challenge. It's going to involve the product rule. I'm sure I'm going to go into another piece of paper using this one, but I think what we should do at this point is take a little break. And after our break, we'll come back and we'll go fresh right here going into this. I'll leave this here. I recommend, if you feel a little ambitious, get a paper and pencil and see if you could go ahead and figure out the answer to this. I'll also leave you those important rules as part of the, don't forget the derivative of a natural log of x is 1 over x. See if you could get some of those. So right now it's 5:40. We're going to take a break until 5:55. And in 15 minutes, we'll come back. I'll explain how we're going to do this, and then I'll show you the rest of the lesson involving derivatives of e to the x. Okay, so students, we're going to return at 5:55. Thanks. Welcome back, students. This is the answer that I got for this question. I want to briefly review how we came to this answer. I don't want to spend too much time on it because it's a lot of advanced algebra. But this is what we got as our final solution for the answer. Let me explain where it came from. It might be a little bit nicer to have this kind of come down to here, actually looking at it. Starting with considering that if we wanted to take the derivative of this, it would start with, of course, rewriting this. You could rewrite this because of this exponent here. You could rewrite this to be this way: f of x equals 4 times that whole natural log of that whole thing. Okay, and that's just an equivalence. That's not a derivative. That's one of the log rules that we talked about. After you have that, you can ignore this constant and then go in there and take the derivative of what's inside. It gets complicated. This is an advanced one. When you take the derivative of what's inside, derivative of a logarithm is going to be 1 over what's inside. But 1 over a fraction means the reciprocal of the fraction. That's why when you do actually take the derivative of it, it's going to be this, but the reciprocal of it. So the derivative looks like this: f prime of x looks like 4 times that whole equation, that whole fraction, but upside down like this. Then we have to take the derivative of this stuff, what's inside right here. And if you were going to do that, I took a separate piece of paper and did that. Here's your quotient rule of how you would go about doing that. You start by saying this is f and this is g. If this is f, then I have to consider the cube root. I forgot the cube in there. I have to get the cube root as a 1/3 power and then follow with f prime in that way using 1/3. Consequently, because of the chain rule, when you do this, you have a 3 that cancels out and it winds up canceling out very nicely. But in the meanwhile, you have the uncomfortable idea of 1/3 minus 1. Don't forget, when you subtract 1 from a number, it's the same as any number on top of itself. It could make it 3 3s if you want. That's why 1 minus 3 is -2. You could do it that way. So anyway, that's why -2/3 is our new exponent. Likewise, the derivative of what's inside here is 3, and the 3 cancels out with 1/3, leaving us with this for f prime. So now we have f prime is this expression, f is this expression, g is this expression, and of course the derivative of x squared is simply 2x. And if you put that all together using the quotient rule, it looks like this. And you can see it's a long story. I would maybe, in rewriting it, take this 2x and put it right in front, right there like that. But I would take this whole expression the way you see it and write it right here after. So friends, imagine that that whole thing that you see there is in that position. I'll leave it there for a minute in case you want to look at it and think about it. So that's everything we need to know about logarithmic stuff, doing derivatives with logarithms. Let's see what else we have in our examples. Okay, so these are the applications. The applications involve a story associated with something in economics or something in one of the social sciences. Example 4 says lifespan. Assume that the average lifespan in years for people born from 1920 and projected to 2020 can be modeled by this function. X is the number of years past 90. Find the function that models the rate of change. What that means is take the derivative. Next, does this function have a maximum value for x is greater than 0? And you can do that with a graph. And then evaluate the limit as x approaches infinity of this. And what do the results tell you about the average lifespan? Now, when we do this question, we're not going to have to do answers for B and C. When you go into WebAssign, you won't see questions associated with parts B and C. However, we still need to know how to do part A, and we need to know a little bit about what they're kind of asking about for B, C, and D. In this one, we're asking you to find the derivative, and when you find the derivative, it's going to be I prime of x, and it's a funny letter I, but in this case it's I. And the derivative of this is a constant here, so there's nothing. The derivative of that is nothing. And then here we have another constant times the natural log of x. Well, the constant rule says I can just write the constant and forget about it for a minute and then do the derivative of this. The derivative of this is 1/x. Does it have a maximum value for x is greater than 0? Well, if we graph it, let's take a look and maybe we can answer. See if I could graph this. Y equals 14.244 over x. And take a close look at what happens as I carry on toward infinity. And take a look at what happens as I approach 0. So the question was, does the function have a maximum value for x is greater than 0? Take a look. When x is greater than 0, x could be 3, 4. These are places and points where x is greater than 0. Of course, here this is not it. These are negative x values. Is there a maximum? And you know that there isn't, because this blue line will never quite cross that x-axis, that y-axis rather. See, here we have an x value of 94. We could carry on all the way up and really go for a really extreme example, and you'll see. Get left side of it. Yeah, I guess I can't get up there. There it is. Well, I guess it's not letting me do it, but anyway, the point being that as you carry on towards in this direction, you'll never get a positive. You'll never get a maximum for your y values, and you could see that it gets higher and higher. 6.4. It'll go up to towards infinity. Is the idea. In this example, we're also asked to evaluate that limit, and does it have a maximum? What is the limit as x approaches infinity? Well, as x approaches infinity for this picture, let's let x approach infinity. Now that's a little bit different. Before we're talking about a limit otherwise, but now as x approaches infinity, you'll see as x gets larger and larger, what's happening is the y value is getting closer and closer to 0. Look. And last, it says, what do these results tell you about the average lifespan? That, of course, it changes with time. So, for example, 4 with the lifespan, the most important thing that I really want you guys to try to remember about that is when you see a question with a model this way, let me get this. When you see a question with a model this way, just remember to adhere to the letters they're using. They're using capital I. Make sure you're using capital I because it'll be incorrect. And then also just look closely at the questions. You won't see things like that B, C, and D when you're doing your website homework, but you will see cases where they ask you for things like the number of years past 1900, what happened in 1980, you have to put 80 in for X and such. Okay, hope that that's clear. For the next example, for cost, it says, suppose the cost function for X skateboards is given by this function, and C of X is in dollars. Now, can you find the marginal cost when 100 units are produced? Explain what that means. What that means, of course, marginal cost, you got to go and find the derivative of that function. Then when you're done, you'll substitute in 100 there. What does that look like? Well, I've got that here for us. Here's the cost function. Let's figure out now what the marginal cost is. C prime of X. Here, this is a constant, so there's nothing there, right? And here we have a case where we have a multiplier times a natural log. I'll make the multiplier the coefficient and ignore it. Now the natural log of this, the derivative of that is 1 over that. And then the derivative of what's inside is 4. So to simplify a little bit, I can take 615 times 4 on top and take the bottom being 4x plus 10. You might be able to see in your mind's eye that you could factor the bottom by taking a 2 out like this. And then on top, of course, 615 times 4 is like times 2 times 2. So the 2 and the 4 cancel, leaving a 2. And your final cost function then is going to be 1230 over 2x plus 5. If you wanted to find the marginal cost at 100 units, you'd put a 100 into the position of x, like so. And you get 1230 over 205. And when you reduce, that does become a perfect 6, doesn't it? Yes, it is. It's 6 exactly. All right. So that is your margin in this situation for your cost in your company, $6. All right. So So carrying on from there, the way that worked was we had a cost function. We were asked to find the derivative of the cost function. It involved a little bit of our new lesson about the log. The natural log of this, the derivative of that will be 1 over that. That's the log rule. And then the derivative of what's inside because of the chain rule, we simplify a little bit. Here's your new marginal cost. Find the marginal cost at the level of production where we have 100 units. We would plug 100 into the expression and we would get our number 6. Now let's talk about something a little different. Let's carry on about, we're going to move away from logarithms now for a moment, and we're going to talk about exponents and exponential functions. In the world of exponential functions, like we said earlier, the most important exponential function is e to the x, and e is that important number that Euler discovered, and it's the base of natural logarithms, and it's used all over the sciences and economics. In the strange case that you have the concept e to the x, the derivative of e to the x is e to the x. And it's kind of funny looking on paper, so I'm going to write a couple of examples of it for you today. the derivative of e to the 10x or e to the x minus 19 or the derivative of e to the something else is just that derivative again, e to whatever it was. Like you see, like a mirror image. However, you have to take the derivative of what's inside, meaning that exponent, using the chain rule. Now, in the case that that you're doing an exponential that's not e, meaning something like 5 to the x or 12 to the x or 1/3 to the x, instead of it being e to the x, it's a number other than e to the x. Then it's basically the same way. You take that thing that you're looking at and just rewrite it. The derivative is what you're looking at. But just to correct it and make it perfect, we add times the derivative of times the natural log of a. And you see that in our bottom rectangle there. Basically, the derivative of a to the x, or for example, 2 to the x, is again 2 to the x, but times the natural log of 2. And likewise, if you have a to the, and it's not x, but it's some other weird expression, then just don't forget to include the chain rule and multiply by the derivative of what's inside, adding another link. Okay, so just the opposite of natural logs. The derivative of natural log is 1 over x. The derivative of e to the x is itself e to the x. So now why don't we take a look at some cases. Here I have examples 1 through 3, and also I would like to share a little bit about example 6. I've went a little bit ahead of us and set up these questions on construction paper. Let's get access to that, and we'll work through them together on the chalkboard there. All right. So remember, the whole concept, friends, is that e to the x has the derivative e to the x. So when you're trying to figure out these derivatives, when you get to times when you have to ask the question, what's e to the x, the derivative is just e to the x. So here for the derivative dy dx, we have 3 times e to the x. Now this first, we apply the coefficient rule, and the coefficient rule says that we can write the 3 and forget about it for a minute, and now just take the derivative of that e to the x. What is the derivative of e to the x? The rule is the derivative of e to the x is just e to the x. There it is. All right, so now look, it looks like we didn't do anything to it, but that is the derivative of it. Okay. Next, what is the derivative of 4x? It's just 4. What is the derivative of -11? It's nothing. The answer this time is 3e to the x plus 4. Great example, introductory about how to take derivatives of exponential functions. In example 2, we have a couple of weird cases using different variables. Let's look at first example 2a. E to the something, the derivative of that is going to be, once again, whatever you're looking at. But remember to multiply by the derivative of what's inside. In this case, the cloud, or what's inside, is that expression 4x cubed. So first, the derivative will be just what I'm looking at. I'll write it just the way I see it. And now I'll multiply by the derivative of 4x cubed, which is 12x squared. Like that. You could simplify a little bit if you want. Looks a little bit nicer if you say it this way: 12x squared e 4x cubed. Make the coefficient be the first thing you see. For example 2b, we're going to flex the muscles of different variables and letters. So we have t and s. ds dt is basically the same thing as dy dx. Don't let it throw you off. But remember that t is like our independent variable, and e is ultimately just a number. And we're going to have to follow those rules. Now, for this one, you'll notice that we do have a 3 there, and we can write the 3 and forget about it and come back to it later. But t times e to that expression ultimately does represent a product. So we're going to have to apply the product rule. The product rule, if you recall, looks like this. Take the derivative of 2 things multiplied. It's in this structure where you prime one of each in that way. For this, we'd say if f, I'll put it here. If f equals t, and g equals e to that, which is a monster, I'm going to run out of room here, then I could find f prime, which would be 1, and I could find g prime. If I had those, I could assemble here what should be written for the product rule. So what I'll do is I'll stop there, and I'll go on over into a product rule case. Like we said, f equals t, and f prime then must be 1, right? But g equals that expression that you see there, e to the 3t squared minus 5t. And therefore, g prime is going to be just that expression that you're looking at again. E to all that stuff. But then times the derivative of what's inside, which what's inside this time is 6t minus 5. G prime is especially ugly this time. Don't let that throw you off. All right, now, if we're going to assemble the derivative using the product rule, what I'll do is I'll try to follow this rule from up here. And I'll do f prime g, which is 1 times g, which is e to the 3t squared minus 5t, plus, now I need f, which is t, times g prime, which is this whole thing, e to the 3t squared minus 5t, times 6t minus 5. This right here is your product, or is your derivative rather. You could try to make it a little bit easier and nicer if you want. For example, maybe the e can get taken out. You'll notice that 3t squared, that this expression does appear here and here. So if you want, maybe you can pull it out. You don't have to. If you did, it would look like this. E to the 3t squared minus 5t times 1, because that would make that come out, plus t, and then you could distribute this t through, making it 6t squared minus 5t. And in descending order, maybe you'd write 6t squared minus 5t plus 1. Where does that belong? That belongs right here. Okay. So like I said, these are pretty complicated little things we got going on here, but yep, that's right. Okay, yeah, it's pretty heavy. So anyway, that's what we would be looking at in a case like that. You could even get rid of this bracket if you want and make it 3e the way you see it. Without those brackets would look fine too. Example 2b was pretty much was really easy there. For example 2c, we're going to be playing around with the quotient rule. Don't worry, it's not that heavy. There is actually a way to make this a little bit easier. You could change this if you wanted to into a product rule by making it negative 3w, and some students would prefer to do that. But anyway, this is a quotient. Most people would look at it as a quotient. So let's apply the quotient rule. With the quotient rule, you'd have f over g when you take the derivative is something like this. So I would say f equals u. That means f prime is 1. And g equals e to the 3w. So g prime is, of course, e to the 3w. But don't forget times 3. So let's just write it this way, 3e to the 3w. All right, so I've got f prime, g, and g prime. Now what I could do is I could write out what I think the quotient rule will give for the derivative. So it's f prime, which is 1, times g, which is that expression. So that's e to the 3w. And then I have minus f, which is u, times g, which is that expression. Oh, g prime, which is that expression. So it's 3u, e to the 3u, all over g squared, which is e to the 3u quantity squared. Okay, now I do have e to the 3. Is it u? No, it's w. That's minus 3. That's the f. Is u. Oh, f is w, not u. Sorry, that's the problem. F is w. Okay, that makes sense, w. So it should be w here. So now what you have is e to the 3w here, and you also have e to the 3w here. Notice that. So you can factor that out. And you can make it look like this. E to the 3w times 1 minus 3w. And then when you have that over e to the 3w squared, this funny thing happens where this is really like e to the 6w, and you're left with the 6w and 3w cancel out, leaving 3w on the bottom. So your final looks like this, 1 minus 3w all over e to the 3w. In this case, and when you play around with e, usually it does simplify to something very nice like this, whereas the other ones are just big, ugly messes of algebra. Here, this does kind of simplify a little bit nicer. And now, to get your solution, try to simplify it down to something like that. Okay, that's e prime. For example 3, we're going to apply the chain rule. But before we do that, I'm going to rewrite this right here to be 2 ln x. And I can do that if I want. It's a little bit easier that way. So that means that e prime is going to be, rather that y prime is going to be just what you see there. But don't forget to multiply by the derivative of what's inside. So let's rewrite that again. E to the 2 ln x. And then what is the derivative of 2 ln x? Well, the derivative of that is going to be, of course, 2 because the coefficient is 2. And then the derivative of ln of x is 1 over x. So this turns out looking like this. 2e to the 2 ln x all over just x. So these all kind of simplify nicely, and you should get comfortable with your mechanics and how to write math out that way. Okay, friends. I hope example 3 was clear. Let's move on to example 4. In 4a and b, we have a situation. It's an application involving investment. Let's take a look at that. Okay, so when $100 is invested at 8% compounded continuously, the amount that accrues after T years, which is called the future value, is as you see here. At what rate is this money in this account growing? At the end of 1 year and at the end of 10 years. Here's the function. If you want to know at what rate it's growing, that means you want to find the derivative of it. So let's find the derivative of it. S prime of t, we can find quickly and easily because this is just a coefficient 100, so I can write it and ignore it. And then the derivative of e to anything is just e to whatever that anything was. And of course, don't forget to multiply by the derivative of what's inside, which this time is 0.08. And then you can use your commutative and associative properties to realize that 0.08 times 100 is actually 8. The answer is 8e to the 0.08t. If you'd like to know what the rate of change is at the end of 1 year, you would plug a 1 into that position. So it will become 8e to the 0.08 times 1, and the calculator will give you an answer for that. Likewise, you could use the number 10 in there, 8e to the 0.08 times 10. And that'll give you the answer as well. Okay. Now, I know you know how to use a calculator to get it, so I'm not going to drag you through it, but that's what you would do for that part of it, friends. Okay. In our next application, we're talking about North 40 Incorporated. North 40 Incorporated is a manufacturer of wilderness camping equipment. The revenue function for its best-selling tent, the Sierra, can be modeled by this function, where R of X is the revenue in thousands of dollars from the sale of X thousand Sierra tents. Find the marginal value when 75,000 tents are sold. Now, let's remember, friends, it's asking you about 75,000 tents, but X is already in thousands. That means that you're going to need to figure out first, of course, the marginal revenue, which is the derivative of this function. And then when you're through, you're going to need to find that revenue, that marginal revenue at X equals 75, because it's not just the number of tents, it's the number of tents in thousands. And if there are 75,000 tents, then X is going to equal 75. Okay, this is what it would look like if you were trying to do it on paper. Here's the revenue function, and now I'm going to find the derivative of the revenue function, R prime of X. First of all, notice this is a product rule, but before I do the product rule, I will just write that 250 and kind of ignore it. In the case of the product rule, I would say f equals x, g equals e to the 1 minus 0.01x. So f prime equals 1, and then g prime is going to be that expression, e to the 1 minus 0.01x, times the derivative of what's inside. The derivative of this funny expression, derivative of 1 is nothing. The derivative of this is negative 0.01. In other words, g prime is the very uncomfortable negative 0.01 e to the 1 minus 0.01x. I'm going to write one more time over here because it's kind of hard to see it. G prime is negative 0.01 e to the 1 minus 0.01 x. Okay, it's important to make sure you have that really clear because it's already small writing and it's complicated, ugly writing. So anyway, we're going to do r of x equals 250 times, and then in here, I'm going to go ahead and find the derivative using the quotient rule, which is rather the product rule, which is the derivative of two things multiplied looks like this. And now I have f prime, which is 1, times g, which is this expression, e to the 1 minus 0.01x, minus f, which is x, times g prime, which is this expression, negative 0.01 e to the all that. And it's all over g squared, which is all of this squared. Okay, so this simplified is going to give you the answer of what goes in here. It's a lot of math in that, and I recommend you take it very delicately. Get comfortable with those decimals, and if I can help you with it, I'll go over some questions with you when the time comes. I don't want to carry on too much about this question, but if you look closely at the actual question with me, it's not actually saying find the marginal revenue. This is the marginal revenue here. It's saying find the marginal revenue when it's 75. In other words, that very, very complicated, ugly that really complicated, ugly expression that we come up with all the 0.01s and the x's in it and the e's, all that stuff, they don't even want to see that. They just want to see the answer when you put 75 in all those x spots, what do you get? So you won't have to enter all of this nasty stuff into WebAssign, which is a relief because it's very complicated and easy to mess up. But if you have it on paper and you're able to use a calculator and you're very careful, you should be able to get it right, putting the number in. Okay, this is what they mean when they say quantitative analysis. This is some very complicated counting and figuring here. There are a couple of examples here that I accidentally did not go through with you. I didn't even realize I had missed them, but they're short, and it is important that we discuss them. And you're still mine for 20 minutes, so I've got to get through these with you as well. Let's look at examples 3 and 4. I skipped them. I didn't realize I had skipped them. For example, 3, we're finding a derivative of something with e in it. So for example, 3, I got y equals the natural log. Oops, sorry. I have y equals e to the natural log of x squared. Okay. So find y prime. Now, if you're going to find y prime for something like this, remember that e to the power of anything is just that again, but then you could take the derivative of what's inside. So one approach here is to just say, well, okay, I know what y prime is. It's just what I'm looking at. But then times the derivative of what's inside, which is 1 over x squared, and then times 2x. And that all cancels out into funny, weird stuff. But before you did all that, you might have remembered that there were some little rules that we could use here. For example, I might want to rewrite this to look like this. and then rewrite that to look like this. And you remember what this is. What is e to the natural log of x? It is 1. And what is 1 squared? It's 1. Now what is the derivative of 1? It's 0. So this is a great example of when should you use the log rules or the exponent rules, and when should you just go right forward. If you did all of this work very carefully, you would wind up with a bottom line of 0. But if you didn't, if you saw the trick, you might be able to get through it quicker and easier. The other examples involve the case where you have a to a power. We haven't done anything like that. For example, what if y equals 4 to the x? If y equals 4 to the x, then your derivative is going to be y prime equals 4 to the x. But then don't forget to multiply by the natural log of 4. And last but not least, ask, is there a derivative of what's inside? The derivative of x is 1, so there is no derivative further to talk about here. This is example 4a. Example 4b, a little bit more complicated. I'm sorry, it's 6. Yes, not 4, it's 6. 6. And that's going to be y equals 5 to the x squared plus x. All right. So the derivative, of course, is going to be 5 to the x squared plus x. But since this is an exponential and we have a base other than e, first of all, I definitely need to include natural log of 5. But then besides that, the derivative of what's inside, this time that's 2x plus 1. The nicest way to write something like this would be to actually put this piece at the end and write something like this. Natural log of x times, natural log of 5 times 2x plus 1 times 5 to the x squared plus x, like so. Right. All right, those are the last couple that I really wanted to make sure I went through with you because I don't know how, but they slipped my mind. All right. In closing, students, thank you so much for your close attention to my lesson. I think you could see it's some complicated material. I tried to make it as clear as I could for you. Now it's in your hands, and you have all weekend to go through all the 11.1 and 11.2 homework, and also to go through the homework from chapters 9.7 and 10.1. When we get together on Monday next week, we're going to carry on with chapter 11.3. The good news is chapter 11.3 is relatively short, so there'll be a significant amount of time during that day in class to go over any and all questions you might have about the homework. Likewise, next week on Wednesday, we have an optional meeting because on that day, we have an exam review if you have questions. And then Thursday next week is your exam, of course, and that's the 28th. So that being said, we're going to end our meeting here. Thanks for your attention, and we'll see you guys on Thursday.